It's Christmas. Let's talk about snowflakes. Hey guys, welcome to eMath. Today I'm going to show you something very cool, which is the Koch Snowflake. First, we'll start with an equilateral triangle. An equilateral triangle. Then we divide into 3 equal parts. Then, for each side at the middle segment, we'll draw a smaller equilateral triangle. A smaller equilateral triangle. Then we erase this part here. As you can see, from an equilateral triangle, we get something like a star, right? The next thing we do is we divide each side into 3 parts again, including the original black side, divide into 3 parts again. 1, 2, 1, 2, 1, 2, 1, 2, 2, 1, 2. Then we'll draw smaller equilateral triangle, or we call it bumps, for every one of them. This is your Christmas present. Smaller bumps. Then we'll erase the part inside. So this is what you got after the 3rd iteration. And of course you can continue to do this, draw smaller bumps, blah 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 blah. At the end you'll get something like this, which looks like a snowflake, isn't it? So what is so special about this shape, or this Koch snowflake, is that number 1, it is a fractal, which means it will look the same regardless of scale. Meaning, if you zoom in, you'll get an equilateral triangle with smaller bumps. Zoom in again, smaller bumps. Zoom in, smaller bumps. Zoom in, smaller bumps. So the shape or the pattern will look the same if you zoom in or zoom out. You'll get something like this. And if you do it for infinite many times, you'll get something like a snowflake, right? The second cool fact about this shape is that it has an infinite perimeter. Does it make sense? We do it for infinite many times. We have infinite smaller bumps, so it kind of makes sense, right? But don't worry, I'll prove it to you now. Okay, so let's redraw the shape. Okay, we started with an equilateral triangle. Equilateral triangle means all the side length are equal. Let's call it L. And this is on the first iteration, so we call it L1 is equals to L. Okay. Then what will be the perimeter? The perimeter will be 3 times of this, right? So P1 will be 3 times of L1. Then for the second iteration, we divide into 3 segments, 3 equal segments. And now it will be a L over 3. Then we draw our smaller triangle, smaller bumps or triangle. And what will be the perimeter? I mean the length that grow from this original black side here. So you can see we have 1, 2, 3, and 4. We have 4 times of L over 3. So it will be L2 will be 4 times of L over 3, which give us a 4 over 3 L. So what will be P2? The perimeter of the second shape. It will be 3 times of L2. So it is actually 4L. And if you notice, from P1 to P2 is actually we multiply by 4 over 3, right? Okay, don't worry, we'll do it for the 3rd iteration. Again, we'll divide into 3 segments, or I directly draw the smaller equilateral triangle, all the bumps. So what will be the length of one of these? It will be a L over 3, then we divide by 3 again, right? So maybe I write 1 over 3 times L over 3. Okay? Then how many do we have for one red side here? We have 1, 2, 3, 4. 4 of them. Multiply by 4. Then how many this kind of structure do we have from one black side. Yeah, we have 1, 2, 3, 4. 4 of them. So we multiply by 4 again. So this is the perimeter that grow from one black line in the equilateral triangle, which is our L3. Yeah, this will be our L3. And this is actually 4 square over 3 square of L, which is 4 over 3 square L. Yeah? And again, your P3 will be 3 times of L3, which is 3 times 4 over 3 square L. And again, this will be 4/3 of P2. Yeah? So since we are doing it for infinite many times, let's try to compute what is Ln and what is Pn. Well, I think you will notice that because this shape here, what we have here, is similar on what we have from the first direction, right? It's the same. So actually Ln, if you notice the pattern, this will be to the raised to the first power, and this will be a 4/3 raised to the 0 power. So we can say that Ln is actually 4/3 of n minus 1 power times with L. And obviously your Pn will be 3 times of this, 3 Ln, which is 3 times 4 over 3 n minus 1 L. Yeah? So actually you can try to compute this using the geometric progression, or you can do it like this. Okay. Remember, we are doing it for infinite many times, which means your n here will approach infinity. You do it for infinite iteration. Yeah, you have infinite smaller and smaller bumps. So we are taking n approach infinity. So the perimeter of this shape here will be the limit as n approach infinity of this expression here, 3 times 4 over 3 to the n minus 1 times with L, where your L here is actually a constant which depends on the side length of your first equilateral triangle. Yeah? And as you can see from here, your n is on the exponent. So if you sub in this infinity, you'll get a very big present. You'll get a very big number, which means it will be a positive infinity. And therefore we say that the perimeter of this shape here is infinite. I hope you are convinced that this shape here has an infinite perimeter. But the next thing I'm going to show you is even cooler. It has an infinite perimeter, right? But it has a finite area. Do you believe it? Well, just come to think about it, right? No matter how many smaller bumps you add to this shape, you are adding smaller and smaller area to it, which means the area of the whole shape just can't exceed the area of this circle here, right? So we can say that the area of the whole shape depends on the area of this circle here, and the area of this circle actually depends on the area of the first equilateral triangle. And I think I have to draw it clearer. Yeah. So this is actually an equilateral triangle inscribed inside this circle. Yeah. So it depends on the area of this circle. So if you want to prove that this shape has a finite area, our direction is that to express the area of the whole Koch snowflake in terms of the area of the very first equilateral triangle. And I'll leave it as an exercise to the reader or the viewer or whatever. Okay, just kidding. I will do it as your Christmas present. Okay, so let's start with the first equilateral triangle. So we have something like this, right? And we'll use back the L from earlier. So what will be the area of this equilateral triangle? Well, you do have a formula, but let's try to derive it real quick. Okay, so the area of it, you can use the Pythagorean theorem, the Goldgoose rule, or you can use the trigonometry, or you can use the semi-perimeter formula. there's tons of ways that you can compute this area. And for now, I'll use the half AB sine C formula. It's the easiest for this, right? Because I know that this is an equilateral triangle, which means the area here, the angle here will be 60 degrees. So I can just type half LL sine 60. And what is sine 60? We have a L squared over 2 here. Sine 60 is root 3 over 2. So we'll have a root 3 over 4L squared. Yeah, so this is the area of the first shape, which is A1. And for the second shape, like I said earlier, we are actually adding the area of the smaller area to it, right? So we just need to find the area of this one smaller triangle. Okay? Again, this is an equilateral triangle. And what is the length now? It is L over 3. So the area of it will be root 3 over 4 times L over 3 squared, right? And how many smaller triangles do we have? We have 1, 2, and 3 of them. We just multiply it with 3. And this is a 3 square here actually. So 3 and 3 can cancel. We have a square here. Okay, ignore this one. So it's actually root 3 over 12 times L squared. Okay. So A2 will be the area of this part, which is A1, plus with the total area of new triangles, which is root 3 over 12 L squared, and which is root 3 over 4 L squared plus root 3 over 12 L squared. Yeah? Then we do it again for the third shape. Okay? Very quickly. 3, and the red triangles. Yeah. Okay. So the area of one red triangle will be root 3 over 4 multiplied with L over 3, then divide by 3 again, which is L over 3 squared. Okay? So yeah, I think I'll write here. We have the area of one triangle is root 3 over 4 L over 3 square. Then we have 1, 2, 3, 4. 4 from each side. Okay? 4 from each side. Then we have 3 black sides. Okay? Times with 3 again. And this 3 and this should be a 4th. This should be a 4th. After cancel, you'll get a 3 to the third power. Get a 3 to the third power, and this 4 and 4 can cancel. This is a L squared, ignore this one. So A3. So A3 will be A2 plus with this root 3 over 27 L squared. Yeah, which is root 3 over 4 L squared plus root 3 over 12 L squared plus root 3 over 27 L squared. And I think you can see the pattern there, right? It's a series. Maybe we try to do it for a few more iterations. Yeah. Then for A4, it is A3 plus with, we have 3 black sides from the first shape times, for each structure like this, we actually have 1, 2, 3, 4. Yeah, 4. And for the fourth shape, we actually have 1 layer. For the third shape is 1 layer. Then second layer. Okay, you'll notice that it is actually 4 to the first power here. Okay, so it's 4 square multiplied with the area of one triangle like this. Again, it is an equilateral triangle. So it is root 3 over 4 times something squared times something squared. The something here is the side length of the smallest triangle. So from here is L over 3, L over 3 squared, then you divide by 3 again, which is L over 3 cubed. So A5 will be very easy. A5 will be A4 plus 3 times 4. 4 to the first power, 4 to the second, 4 to the third, times root 3 over 4 L over 3 to the first power, 3 to the first power, 3 to the second power, 3 to the third power, 3 to the fourth power. Then you square it. And you can do it for infinite many times. Okay? So from here we can conclude that AN is actually A n minus 1, which means the area of the previous shed, plus with the area of the total smaller triangle or bumps added to the shed, which is 3 times 4. This should be a n minus 2 times root 3 over 4 of L over 3. This should be a n minus 1. n minus 1 squared. Okay, as you can see, we have a recursive definition here, which we don't want. So we try to write it in terms of sigma notation. Okay. So the first thing we do is we try to factor out this L squared, because we know that for every term, for every area, we definitely have an L squared. So we factor L squared, then times with the area of the first triangle, which is root 3 over 4 times L squared, then plus with the summation from k, we start from the second shed, okay? Then we will try to reindex it later, okay? K equals to 2 to n of, okay, we can take this 3 root 3 together, and perhaps maybe I should put it outside, but never mind, times with 4n minus 2, okay, 4n minus 2, then you divide by 4 again, which means it is 4n minus 2 times 4 minus negative 1, which is 4n minus 2 minus 1, which is 4n minus 3, okay, 4n minus 3. Then this is a 3 square n minus 1, which is 9 to the n minus 1 over 9. Oh, sorry, it should be a k minus 1. Okay, sorry, this should be a k. Okay. So this is the an that we have. And remember, we do it for infinite many times, which means we are taking a infinity, which is L squared times root 3 over 4 plus, okay, we take out this 3 root 3 from k equals to 2 to infinity of 4k minus 3 over 9k minus 1. Yeah. And for now, we just need to compute this series here. Okay? I'll clear some space. As you can see here, this is actually a geometric series. So my goal here, the easiest way to compute this is to use this sum to infinity formula, which is a over 1 minus r. Okay, where your a is your first term, r is the common ratio. But to do this, I need to express it in terms of something like this, right? K equals to 1 to infinity, something, where your something here, your common ratio should be smaller than 1. And I mean it is the absolute value of it. So we need to re-index it to make it start from k equals to 1. Okay? So yeah, it is k equals to 1. Now we start from 1, which means it's 2 minus 1. So we need to add 1 to the k in this expression here. It is 4k plus 1 minus 3 over 9k plus 1 minus 1. Okay? Then it should be a k equals to 1 to infinity of 4k plus 1 minus 3 is k minus 2 divided by 9 plus 1 minus 1 cancel out each other, 9k. Okay, so to make our life easier, I will try to factor out this 4 to the negative 2 power, which means it is 1 over 4 squared, which is 1 over 16. Okay, it is 1 over 16 of, okay, this of, and now we already have 4k, right? So we can write this together, k. Yeah, very nice. And we can use the formula now, which is 1 over 16. The first term is 4 over 9 raised to the first power, which is 4 over 9 over 1 minus, what is the common ratio? The common ratio is 4 over 9. So we try to compute this. Okay, so this should be a 4. This one divide is a 1 over 36 over, this should be a 5 over 9, which is 1 over 36 times 9 over 5. This is a 4, 1, this is a 1 over 20. So we know that this series here is actually, well, converged to 1 over 20. Last thing we have to do is to simplify this, and see if we can express it in terms of the area of the first equilateral triangle. Let's do it real quick. Okay, A infinity will be L square root 3 over 4 plus 3 times root 3 of, we know that this is actually 1 over 20, right? Okay, so this will be a L square times root 3 over 4. Okay, let's do it like this. Plus 3 over root 3. And 20 is actually 4 times 5. Okay, because I want to factor out root 3 over 4. Okay, and we will have a root 3 over 4 L square of 1 plus 1 over 1 plus 3 over 5, which is root 3 over 4 L square times, this should be a 8 over 5. Remember, root 3 over 4 L square is the area of the first equilateral triangle. So A infinity is 8 over 5 times with the area of the first triangle. And we are done. Alright, that's all for today. I hope you like my Christmas present, and Merry Christmas! 走れソリよ風のように月見原をパドルパドル Oops